Hello, welcome to the Introduction to Partial Differential Equations revision tutorial. Before we begin, I just wanted to go through a few points about what to expect from this revision tutorial. So the idea of this revision tutorial is that this is a study aid, not a study substitute. Each section tries to highlight some common theme. So in this course, many ideas and techniques are repeated in the different sections. And the purpose of this revision is to highlight this so you can recognize what the themes are. But what is examinable is in the script and with a focus on proofs. So the idea is that this revision tutorial should be used in conjunction with the lecture recordings and the script to help you access that material better. In particular, I would encourage you to find the copy of this presentation and make your own notes as we go along. And when we have exercises in this presentation, to pause, try the exercises yourself first, and then come back and we'll do them together. I've not been comprehensive in this revision tutorial, by which I mean not every single point from the lecture script is covered. And also the order is not covered. So the order is not preserved. So it might jump around a bit. This is so that I can highlight what's common between different sections. Just a small note, if you see references like S1.1, that means section 1.1, and X1 is exercise 1 from the sheets. Okay then, let's begin. So what is a partial differential equation? This you probably know. These are equations whose solutions are functions, and those functions, their partial derivatives, must obey a certain relation. Okay, so this means necessarily that these are functions of multiple variables. Often, partial differential equations come from physical problems in physics, though it is used across all sciences. In particular, some of the partial differential equations we study, such as the heat equation and the wave equation, obviously come from physics. In that domain, the variables are usually time plus space. So you're looking at some quantity that is different at different points of an object, say, and also changing in time. So this is different to an ordinary differential equation, which depends only on one variable, which typically is time. So you might be looking at how some quantity changes over time, but there's just one thing you're looking at here. Here it's there's not so much a unified theory of PDEs, rather than some common techniques that apply to different equations. But each equation tends to be its own subject of study, with particular things that are special just to it. And that's the focus that we take in this course as well. But there are some common things you want to know when you look at a partial differential equation, and they might be summed up as regularity, existence, and uniqueness. Okay, let's begin with regularity. This is often overlooked or not talked about so much, but is in fact very important because what sort of functions can be solutions or are allowed to be solutions. So this might be an obvious point, but if you have a partial differential equation with a second partial derivative with respect to time, say, then the solutions probably should be twice differentiable with respect to time for the partial differential equation to make sense. But we have seen in this course that we will also look at more general solutions, and so this opens up a larger class of functions. And so there might not be a solution in the smaller class of functions, which say twice continuously differentiable, but there might be solutions in the larger class of functions, say functions that are just continuous. So regularity really sets the stage, or is part of the ingredient for when you have a partial differential equation, what are you even looking for? So now that we know what we're looking for, obviously the question is, does there exist a function? This is existence, which is a solution. But in existence often includes boundary values. So the partial differential equation might hold on the interior of some domain. Typically, we call it the domain omega. But we might require that the function have certain values on the boundary or obey some other conditions. And so then existence becomes not only can you find a function that satisfies the partial differential equation on the interior, but also has the specified values or conditions at the boundary. So that makes existence sometimes a bit trickier. Or it can also mean that there can be multiple existence questions, depending on which different sorts of boundary conditions are given. And then that obviously ties together with uniqueness, in that we, given some boundary value conditions, is there existence? And if there's existence, how many solutions are there? If there's only one, then of course we have uniqueness. So this is one way to think about uniqueness. The other way to think about uniqueness and boundary values is that we're trying to set up the problem in such a way that the solution is unique. So what data is necessary to be given on the boundary such that there will then be only one solution? So the analogy I would have to here would be, consider the very simple differential equation y prime is equal to y. So this is an ordinary differential equation. Of course, it has the solutions. Y of x is equal to a e of x. Okay, so here we have a ordinary differential equation, and we found all the solutions. So there exists the solutions. What I mean is, we see that the boundary value, a0, which in this case is a, is in one-to-one correspondence with the set of solutions a e to the x. So by saying that we give, in this case, a boundary condition of the value of the function at 0, this is making it into a unique problem. Right? If we just consider the equation, then there are many solutions. If we impose this sort of boundary condition, then we have a unique solution. We could also give the value of the derivative at 0, because this is also the number a, and then that would also give one-to-one correspondence with the space of solutions. So there are multiple ways of setting up the problem, giving different sorts of boundary values or conditions, such that these boundary values parameterize the space of solutions of our equation. And we'll see that sort of thing when we go into more detail as well. So that's part of uniqueness, choosing boundary value conditions such that we have a unique condition, not just is there a unique condition or not, a unique solution or not. And then having answered the question of does there exist a solution and is that solution unique, we then come back to regularity again. So we can ask, from the solutions we found, we were looking, say, among functions that were twice continuously differentiable, and we found some solutions. Does it actually turn out that those solutions are more regular, have more derivatives, or better behave functions than we assumed at the start? And so for Laplace's equation, this is the case, that the only twice continuously differentiable solutions to Laplace's equations are in fact smooth functions or analytic functions. So the regularity was better than we assumed at the start. So regularity sort of comes at the beginning and at the end, with existence and uniqueness in between. So those are the main questions we ask of a partial differential equation. And as we go through and look at different partial differential equations, you can understand somewhat what we're doing is answering these questions of regularity, existence, and uniqueness. We've seen, so I'll point out some particular example. in section 2.3 of the lecture script, that's here, existence of solutions, there is actually this example of a partial differential equation that is nowhere solvable. So there is no function that obeys this partial differential equation, and this is really strange. So existence can be quite a difficult thing for partial differential equations, is what that section is pointing out. And 2.5 is talking about the different sorts of regularity that a function can have. All right, continuous, differentiable, continuously differentiable, smooth, analytic, and also whether it's integrable, whether it's L1, whether it's LP, integrable, and so on. Okay, so there are many partial differential equations. We try to classify them, so we carve down the problem and we look at particular subproblems and particular types of PDEs to look at. So the most important one is order. Hopefully you've, listening along, now give the answer to that question. What is order? Order is the highest derivative that occurs. Same as for ordinary differential equations. So in this course, we look at first and second order PDEs. So section 1 deals with first order PDEs, and there's this theorem that basically shows you how to solve all first order PDEs with the method of characteristics. And then we look at 3 particular examples of second order PDEs. The other important thing is whether the equations are linear and or homogeneous. So whether an equation is homogeneous really depends on linearity. It only makes sense for linear things. So we can look at a differential equation. Let's just write one. Say the t derivative of u minus the x derivative of u should be 0. What we do is we think of the t derivative of a function minus the x derivative of a function as some operator L. And so then the question is, because it acts on a function to give another function, and the equation says that this other function should be u. So a PDE is linear if when you write the operator L and you have u and it acts on, say, the linear combination of 2 functions, do you just get the linear combination of the operator acting on each one of them? Right, so that's what linear means. And then homogeneous for a linear equation is the equation the operator acting on u equal to 0? This is homogeneous. Or is it equal to some other function? And this is inhomogeneous. Okay, so often we treat the homogeneous situation first, and then we treat the inhomogeneous case as an extra addition to this. This is for the following reason, that if you have a linear operator and a homogeneous solution, and let me call this one V, say, and an inhomogeneous solution, then L of u plus V by linearity is L of u plus L of V, which is 0 plus F, which is F. So the sum of a homogeneous solution and an inhomogeneous solution is again an inhomogeneous solution. Or to put this a different way, if you have any 2 inhomogeneous solutions and you look at their difference, then their difference is a solution to the homogeneous equation. So to solve the inhomogeneous equation, what you need to do is find one solution, and then any other solution will be that solution plus a solution to the homogeneous equation. So thereby reducing the problem to the homogeneous case. So that's sort of a general strategy that we employ in this course. And the 3 second order equations that we look at are all linear equations, as well as most of the first order ones we look at, but not all the first order ones we look at. Yeah. So among second order equations, there is a further classification into elliptic, parabolic, and hyperbolic. So the first thing to understand this further classification is we should write down a general second order differential equation. Okay, so what we have here is we have a term that is the sum over I and j in the appropriate however many dimensions, however many variables the function has. And for example, I'll write this out in the case of n equals 2, two variables. We would have a11, the derivative with respect to the first coordinate twice, plus a12, like so, plus a21, 21, plus a22, like so. So we see that every possible combination of second derivatives are represented in a sum of this form. Okay, so the general equation would be a term of a sum of this form plus a sum over all the possible first derivatives plus c times u equals an inhomogeneous term. That's all. Sorry, I should say that's all the linear second order equations have this form. And so in particular, the highest order tends to be the dominant behavior of the equation for linear equations. So we look at this highest term and we try to classify the second order equations by their highest term. So what we have is we have a symmetric matrix here, A. This should be symmetric. And it's symmetric because of the symmetry of the mixed second partial derivatives, A12 and A21, under reasonable assumptions of regularity are equal to each other. So you can always arrange that A12 and A21 or any other pairs of symmetric coefficients are equal to each other. And so we can assume that matrix Aij is symmetric. So that means it has a symmetric matrix, a symmetric real matrix has real eigenvalues. So we have this classification according to the eigenvalues of A. So all the eigenvalues having the same sign. That is called elliptic. All eigenvalues, if I can spell, same sign, except for one, which is 0. This is called parabolic. So we should understand the parabolic case as similar to the elliptic case, except one of the eigenvalues has become 0. So it's sort of a limiting case of one of those eigenvalues moving to 0 of the elliptic case. And then in the third case that we consider, we have only one eigenvalue has the opposite sign to all the other ones. And this is the hyperbolic case. So if you only have two variables, there are only two eigenvalues. So the entire possibilities are the eigenvalues have the same sign. Some of the eigenvalues are 0. All the eigenvalues have opposite signs. But in higher dimensions, there are other possibilities. However, these are the three main cases. And that's because we mostly study partial differential equations coming from physics. And the one eigenvalue, which is different from the other ones, tends to be the time one, the eigenvalue corresponding to the time variable. because obviously usually the problem is symmetric in space, because that's how physics works. Physics, there's no x, y, and z coordinate hanging around us all the time. It's sort of arbitrary. So all the space coordinates should behave the same. And so the corresponding eigenvalues should all have the same sign, except the time one, that can behave differently. So it could be have the same sign as the space ones, be zero, such as in the heat equation, or have the opposite sign. So that's the reason we consider this classification in general, or why this classification is so useful. And because this is an introduction course, instead of studying the full set of elliptic equations or parabolic or hyperbolic equations, what we do is we study one from each of these types. So from the elliptic type, we study Laplace's equation, which is the Laplacian operator equal to 0, where the Laplacian operator is by definition the sum of the second derivatives of all the coordinates with respect to all the coordinates. So if you think about the corresponding matrix here, we just have the identity matrix because there are no mixed partial derivatives. They're all pure second partial derivatives. And so the identity matrix, the eigenvalues are all 1. They all have the same sign. It's elliptic. For the parabolic example that we study the heat equation. Sometimes we put a minus sign here as well. Obviously, it doesn't matter when it's equal to 0, and it's just a convention, but it makes it fit with the heat equation and the wave equation. So if we think about the heat equation now, if we just look at the second order derivatives, there's no second order derivative with respect to time. So if you like, the matrix A, if time is the first coordinate, there's no second derivative with respect to time. So you get a 0 there. And then I guess this is -1, -1, -1, -1, and so on. All the rest, you just have the negative of an identity matrix here. So they all have the same eigenvalues. So in total, we have one eigenvalue of 0, and then the rest are all just plus or -1, depending on your sign convention. And so that is parabolic, right? All the eigenvalues are the same sign except for 1, which is 0. Notice here in the heat equation, we do have a derivative of a lower term, right? So it's not that there's no time derivative. It's just that the time derivative is of lower order and so does not count in this classification of elliptic, parabolic, hyperbolic. And then for the last one, we have the wave equation, which is the second derivative with respect to time of u minus the Laplacian is equal to 0. So if we think about the corresponding matrix A here, we have a 1 for the second derivative with respect to time, and then all the space derivatives are -1. Right, so you have exactly one eigenvalue whose sign is opposite all the other eigenvalues. And so that makes it hyperbolic. And we saw in the course that hyperbolic equations behave really differently to elliptic and parabolic equations. For example, elliptic and parabolic equations have some sort of maximum principle, whereas hyperbolic equations do not have a maximum principle. So if this was a tutorial, normally I would ask you any questions, but I'm in a room by myself. So I will just pause a minute and then we'll move on. Okay. So the next basic idea in partial differential equations is to think about domains and the boundary conditions. All right. So typical domains, they should be open. We want open domains because the definition of a derivative requires taking a limit towards a point, and that limit should be, so the function should be defined on a neighborhood of that point. And so that sort of necessitates having open domains. All right. Often, but not always, we will consider bounded. So sometimes the domains are bounded, and often what we'll see is that there's really good behavior on bounded domains and okay behavior on unbounded domains. Right? But obviously, unbounded domains are also very important. We usually assume that the boundary is a manifold. We often make this assumption because we want to apply the divergence theorem on the boundary, and the version of the divergence theorem that we have, as we'll see shortly, requires that the boundary is a manifold, so we can do the integration on the boundary. Or actually, I should say it's a submanifold, right? Which is obviously a type of manifold. We also have some domains that we look at very often. So we solve some particular cases, right? We also often try to look for solutions on balls, BXR. So, for example, it's very useful for us to solve first the Laplace equation on balls, and then you can improve this to other domains, or determine a lot about harmonic functions from looking at balls. And for the heat equation, we have this special thing called the parabolic cylinder. So if omega is an open domain, an open subset of Rn, the parabolic cylinder is, with the inclusion of time, not including time 0, but yes, including time capital T. And we call the boundary of the parabolic cylinder, so we use this symbol for boundary as well, this partial symbol. And sometimes we put a subscript P to remind us that it's a particular definition for these types of sets. I would draw it like this. But what this means is that you should look at the boundary of omega for times up to T not including time 0, together with the domain at time 0. Okay, so if you like, at time capital T is included in the parabolic cylinder, and so the boundary of the parabolic cylinder, quote unquote, or the parabolic boundary, is all the other parts of the boundary. So the sides for different times, and also the initial condition. So we have this sort of special definition of the boundary of a parabolic cylinder. And those are the typical sorts of domains that we try to solve PDEs for in this course. We also have these special names. We call them problems. So we have PDE, say the Laplace equation or the heat equation. And then we might say we want to examine the Dirichlet problem for the Laplace equation, or the Dirichlet problem for the heat equation, something like this. So we have these names. So Dirichlet problem means that we give on the boundary the values of the function. So if the solution is u, the values of u. Neumann problems that we give on the boundary, instead of giving the values of the function, we give the value of the derivatives of the function, right? In some sense. It can vary exactly what derivatives you give. So in this course, we've almost exclusively looked at Dirichlet problems and not looked at Neumann problems. There are also what's called Cauchy problems. And when I was doing the revision for this, I found two different definitions. So the definition for Cauchy problem 1, that you give both information. So you give both the value and the value of the derivatives. And we'll see that, for example, with the wave equation. Cauchy problems can also mean that you give you give both the value of u at the boundary and the value of the derivative. So yeah, both. That's what is the Cauchy problem in the case of the wave equation. We also sometimes use this to mean the initial condition plus boundary values. And I think this is how we call the Cauchy problem of the heat equation, the initial condition of the heat equation plus the boundary value for when you have a bounded domain. Of course, the initial condition at time 0 is a type of boundary condition, in my opinion. Right? You just have the time 0 boundary as opposed to a boundary in space, but they're both types of boundaries of the domain where the PDE has to hold. So I find this C2 a bit confusing, but nonetheless, people do use this in this way and make a distinction between initial values and boundary values in space. So be aware of both of these meanings of Cauchy problem. Yeah, so typically you don't just want to solve the PDE, as I said, you also want to solve the PDE given some boundary values. And well-posedness is well-posedness is the question of given the boundary values, does there exist the possibility of a solution? So what do I mean by this? So if we look at exercise 31, this was for the Laplace equation on, let's say, the ball, except for the point in the middle. So we're looking at 31A here. All right, consider the ball except for the point in the middle of the ball. And we give the boundary values of this on the outside of the ball and also at 0, because that's the boundary point of the punctured ball. And what we found in this question was, unless the value at the center is the mean of the values on the outside of the ball, then there is no possibility of solution. And if it is the value of the mean in the middle, then it's unnecessary because that information is already contained in the boundary. So this would be an example of a problem that is not well posed, because depending on how you give the boundary values, either you accidentally forbid a solution, or you accidentally prevent solutions from existing, or that some of the information there is redundant, like is not needed. And so well-posed problems mean, can I just give whatever boundary values I want, more or less, or is the problem set up in a way that it's fruitful to solve and you'll get some useful information out of it, or have I accidentally made a quote-unquote mistake in even looking at this problem, right? I should be looking at a different problem that describes this problem or includes this problem as a solution. So people will sometimes ask whether for a particular boundary value condition, the problem is well posed. And it's sort of getting at this issue of whether there exist solutions or whether some of the boundary information is redundant. Questions like that. Okay. So now to close off this section of basic notions, I just want to go through some calculations and then recall some definitions that we assumed for this course. So, of course, everywhere in this course, we use the chain rule many, many times. And so let's just do a revision of what's involved in the chain rule. So the chain rule, as you might know it from analysis 2, says that the derivative of the composite of two functions at some point x is the derivative of f at g of x composed with the derivative of g at x. So this is a nice abstract statement, but it's relying on a very particular way of thinking about the derivatives, and it's a bit more abstract than we would normally use when we're just doing partial derivatives and the chain rule. So let's start with this and then see how you get back to something useful for this, useful to actually apply and calculate with. So the first thing to note is that we're thinking of this as a linear operator. And so when we actually want to do calculations with linear operators, we should write them as a matrix. Okay, so as a matrix, the linear operator of the derivative of a function at a particular point is the matrix of partial derivatives. And the composition of two linear operators when they're written with matrix is matrix multiplication. Okay, so that's how you actually do calculations with linear operators. You write them as in a matrix form, and then you do matrix multiplication to compose them. So what is the matrix that corresponds to a derivative? If f has several components and is derived with respect to several variables, it goes like this. No, one goes across. Maybe I'll put some dots, dot, dot, dot. Fn. Sorry, F1 with respect to xn. And then you'll have F2 with respect to x1 right down to Fm with respect to x1. All right, and so here you'll have F2 with respect to x2, and so on, F2 with respect to xn, and the bottom Fm with respect to xn. Okay, I remember this matrix as the things on the bottom go down. Right, so we have x1 on the bottom, so this whole column is x1 going down, and the index on the top, so the component of the function, it's on top, so it goes across. Like so. So we have on the top row all of f1, all of f2, and so on. But that's a total pain to write out. So how can we write this better? We can also write this matrix. What do we have on the top row? We have the first component of f with respect to all the different variables that it's a function of. In other words, we have the gradient of f1. And then on the second row, the same thing with f2. So we have the gradient of f2. And at the end, the gradient of fm. So the rows of the derivative matrix are the gradients of the components. All right. So that's the first part. That's what the derivative is. And then you would evaluate that at gx and matrix multiply that by the same thing with applied to g. But we can be a little bit more, we can say something a little bit more or say something more about the typical case. So let's look at now here, this question 1. So we have u now being expressed in polar coordinates, and we want to take the theta derivative of that. So how do we get that now from here? So firstly, we have to recognize that the change of coordinates is a type of function, right? A change of coordinates is the function of this form. Normally we write r first. R cos theta, r sine theta. So what we really have is we have the derivative with respect to theta of u composed with phi. Right? That's what a change of coordinates is. You compose with the change of coordinates function. And so now we see why the chain rule would apply. And it's going to apply like this. So what do we have? Well, firstly, let's just look at if you looked at the derivative of this thing. So the derivative matrix, what would you have? Well, you would have the derivative of this with respect to each of the variables that's a function of. So that's just by definition of D as a matrix. But by the chain rule, you would have du, not composed, sorry, at phi of r theta. And then I'm just going to use a dot for matrix multiply with the d of the coordinate transformation. So if we continue with that, u is, well, it's not stated here, but let's just assume, as is typical, that u is a real valued function. That means it only has one component. And so it's the derivative of u is just its gradient. And then it will be matrix multiplied by the derivative of phi of the coordinate transformation. Now, as I already wrote up here, normally when we make a coordinate transformation, we don't actually write a letter for the coordinate transformation, right? There's no phi involved. What we do is we write the new variables, x and y, or what we're substituting. These are the components of phi, right? The first component of phi is x, and the second component of phi is y. So instead of writing phi 1 here, I would normally write x, and instead of writing phi 2, I would normally write y. So then what do we see in the form of this matrix? We see that for a coordinate transformation, the columns of the coordinate transformation are x with respect to r and y with respect to r. And the same thing here with theta. So maybe a nicer way of writing this matrix is in the first column, we have the sort of all the coordinates. So the position vector, I'll use the underscore tilde for vector. Or no, I won't. I'll use an arrow on top for vector. And then in the second coordinate, we have all the coordinates with respect to theta. And why this is nice is because now it's easy to read off without writing out the full, without writing out this full derivative matrix. If we only want one component, we can look up what this is straight away. All right, because here we only have one row vector multiplied by this matrix, which has some nice columns. So we'll have here u dot product with the coordinates with respect to the r, and here we'll have u dot product with the coordinates with respect to theta. So we can read off that if we want this, the the partial derivative with respect to theta of the composition. It's just this corresponding entry here, and yeah. So then we can make this into some general rule that if we want for a coordinate change, I'll still use theta here for the coordinate change with respect to, say, the new coordinate yi. This should be the gradient of u dot product with the x coordinates with respect to yi. Right. So this is the general rule if you just want the partial derivative of a change of coordinates. Right, and how it comes from the general chain rule. So let's go ahead and now that we have some formula, apply this in this particular case, right, to u with the polar coordinate transformation. So coming back, that's going to be u of r cos theta, r of sine theta. So we're going to have the gradient of u, so u with respect to x, multiplied by the x coordinate with respect to theta, plus u with respect to y. So this is coming from the gradient, and then y with respect to theta. And so we sort of have this, what you might see from the chain rule in one variable, where you sort of have this fake cancellation between the top and bottom, but it's actually the sum over all possible such things. And again, the first is coming from the gradient, and the second is coming from this derivative with respect to theta. Okay, so we just finished writing this out. Plus r cos theta. All right, and so that is how you calculate the theta derivative of u in terms of its x and its y partial derivatives. All right, so one thing I should note here is that when I write this, I've just been lazy and I've left out the fact that this should be written when you make the substitution in r and theta coordinates, right? So you should still have the coordinate transformation. If I were to write this properly, it should be the partial derivative function with the coordinate change applied, right? Composed with the coordinate change to get the change of coordinates. But almost all the time we don't write this, and it's just implicit that you should also change the coordinates of any partial derivatives or any other function that's written here. So that's how you get the answer. Let's look at the second case, which is, so this was one. The second case, which is the second partial derivative with respect to t, of f of x minus t squared. And this is a very common situation that happens a lot in this course as well, because we use this for the transport equation, and we use this for the method of characteristics, and we use this for the wave equation. So again, implicitly what we have here is a change of coordinates. So we might have something like v, which is x minus t squared. So you have a function f of v, and then we've made the coordinate transformation that v is equal to x minus t squared, like so. So what you should do here is you should do this one derivative at a time. And what does the rule say? The rule says that we should have the gradient of f multiplied by the coordinate with respect to whichever new coordinate we want. So in this case, it would be partial f partial v and then the derivative of v with respect to t, like so. Now, because f is just a function of one variable, the variable v, we would normally just write this as f prime. Okay, and it's f prime of the new coordinates multiplied by minus 2t, like so, minus 2t. And so now we should differentiate again. And not forget that this is a function of t, and this second factor here is also a function of t. So we should apply the product rule or Leibniz rule, and we get minus 2 like so. And then if we differentiate the part with f in it, we'll get another derivative, and we'll get another one of these factors, just like up here. Oops, sorry. Plus f double prime x minus t squared minus 2t squared. Like so. And of course, you can expand this and simplify if you like. So that is how you do partial derivatives, and in particular, the chain rule. All right. You might want to remember this formula here, or you might want to remember this shape here of this general pattern. Okay. So let's continue then. What was new? So I expect you would have seen the chain rule and the partial derivatives before. What is probably new to you in this course was submanifolds and integrals on submanifolds. All right, so you would have seen multiple integrals, so say integrals over an area in the plane or over a volume in space. But a submanifold is integrating over a surface in R3 or over a curve in R2. And obviously, this is not just Lebesgue integration over that set, which would be 0 because lower dimensional sets have measures 0. So they're null sets and their Lebesgue integrals are 0. This is something different. All right. So we make a new definition. So the first part of the new definition is in 2.1. And it is about the definition of what it means to be a submanifold. So a subset is called a submanifold if it's covered by images O of homeomorphisms onto open sets that are continuously differentiable and have full rank. Okay, so what does this mean in a more natural language? A subset is called a submanifold if it's parameterized by a continuously differentiable function of k variables. All right, then it becomes a k-dimensional submanifold. So let's do an example where that is the case. So if we have something like S1, which is the set x squared plus y squared equals 1 inside the plane R2, this is a submanifold because we have, let's say, phi 1 going from acting on numbers between 0 and 2 pi and taking them to, let's say, cos theta, sine theta. My notation is pretty bad here. It should be theta in this set is mapped to cos theta, sine theta. And so what we have here is we have an open subset. This would be U1, which is an open subset of R, so one variable, continuously differentiably mapping onto the set S1, but not all points of S1 are covered. Okay, what is covered? This covers, or I should say O1, which is the part that is parameterized by this, is S1 except for the point 1, 0. So if we think about this drawing, It covers all of the circle except for here. This is O1. To cover the remainder of the circle, we would take a second parameterization, say theta in minus pi pi, and map to, we can use the same formula. It's a different function because it has a different domain. This would be now U2. And then O2, so this is O1. We would have everything except for this point here, O2. And we see that S1 is a union of O1 and O2. And O1 and O2 are parameterized sets. So S1 is a submanifold because it is covered by continuously differentiable parameterized sets. So that's what it means to be a submanifold. All right. And so here, instead of definition 2.3, which is a little bit more complicated, I gave a particular case. If we have a submanifold that's just covered by one parameterization. Okay. So O1 by itself, all the points of the circle except for 1, 0, that's also a submanifold, right? Because it's covered by this parameterization. So if you have a submanifold O, or a set O that is parameterized by one function, then the integral of a function over that submanifold has this definition here. Okay, so what do we have? Instead of integrating over O directly, we integrate over the parameter space U, where the function where the parameterizing function comes from. We compose F with the parameters to make it a function on U. We have a factor here that depends only on the parameterization. And this is sort of how this measures how stretched or how contracted the parameterization is. And then we just do a normal Lebesgue integration over the parameter space instead of over U. Okay, so we use d sigma to indicate the sigma here is for surface or submanifold. It's this special type of integration on submanifolds, and it reduces down to a particular Lebesgue integration on the parameter space. So let's do this example here, where O is part of a circle where y is greater than 0, and the function f is equal to x. Okay, so the first thing we do is we need to get a parameterization that covers O. So we'll take our phi to be from, let's say, theta in U, and we can take U to be 0 to pi, right? Because the part of the circle with y greater than 0 has angle between 0 and pi, and so using the standard parameterization of the circle, it's given by this formula, right? So that covers everything here in O, in the plane. So we have, by definition, the integral over O of the function x d sigma should be the integral over U of x composed with phi. So that's just going to be cos theta, because this is x and y. And so the composition is just substitution here, multiplied by the determinant of the derivative transpose times the derivative. Yes, that's enough brackets. And it's just d theta because the variable is theta and we're just in R, and that's how we normally write the Lebesgue integral on R. So what we need to do is we need to calculate this area stretch factor. So again, we need the derivative. So the prime is just a different notation for the derivative of phi. This is its matrix derivative. Excuse me. And so the first component of phi with respect to theta, and the second component of phi with respect to theta. Now, it's quite important that you get the shape of this matrix correct, so make sure you have in your mind either the rule I told you before or your own rule for remembering what shape the derivative should have. In this case, the derivative is cos with respect to phi, which is minus sine theta, and sine with respect to theta, which is cos theta. So that's what the derivative of phi is. Next, we should calculate the transpose times the derivative. So this will be the transpose is like this, turns it from a column vector into a row vector, and then matrix multiplied by the derivative. And so what we end up with is we end up with a 1-by-1 matrix, which is sine squared plus cos squared. And that is 1. So we end up with a 1-by-1 matrix where the only entry is 1. We now take the determinant. Okay, it's clearly just going to be 1, and the square root is again 1. So continuing on up here, we now have the integral over u, which is from 0 to pi, of cos theta multiplied by 1 d theta. And if you think about the graph of cos from 0 to pi, the areas cancel, and you end up with 0. So that's an example of an integration over a submanifold. Okay, here the submanifold was the top half of the circle, and the function was x. Okay, so that's how you apply this definition here. Let's have a look at definition 2.3 though, because it's a little bit more complicated. In definition 2.3, we already have this thing called a partition of unity. And instead of taking one of these integrals that I've said here, we take a sum over many such integrals. But the difference is, instead of having the function f, we have the function hl times f, where hl are functions coming from the partition of unity. Okay, so to understand the full definition, because not every submanifold is covered by a single parameterization. Sometimes we saw about the circle, you need 2 parameterizations to cover the circle. And so what is this partition of unity thing here? So what a partition of unity is, this is in definition 2.2, but let me just give the easy recap, or the short definition, maybe informal. The partition of unity is a collection, and it actually, we use this weird word subordinate, subordinate to a cover OI. So that means that OI are sets, and the union of all the OI is equal to the space A, for instance. So A is the submanifold in this case. Is a collection of smooth functions. Let's say HI, so that the following properties hold. And HI, I should say, these are functions from the whole space A to 0, 1. Okay, so they're all between 0 and 1. And they have these properties. HI is equal to 0 outside OI. Okay, so the idea of HI is it's only not zero inside of the OI, inside of its corresponding OI. And the other property is at every point of X, if you add up all of the HI, they add up to 1. All right, this is why it's called a partition of unity, because the unity refers to 1 here, and the partition means breaking this up into a sum. All right, so that it's a partition of 1. It's 1 is broken up into a sum of things. These are the essential points. If you look at the actual definition of 2.2, it's a bit more complicated. It has some detail. It has this local finiteness detail. But these are the core principles we want, and the rest are technical details that you should know, but they're technical details to make sure the calculations are all valid. Right? These are the properties that we want. The rest are technical details to make it work. And why does that help? It means that any function on A, any function f on A, can be written as 1 times f, obviously, which means it can be written as a sum of f hi, like this. Right? So every function f is equal to the sum of f times hi. And this is nice is because f of hi is 0 outside of OI. So the idea is that you start off with this integral over the submanifold, you rewrite f as this sum, fhi, over A, and then by properties of the integral, and this is where you need some of the technical assumptions about the finiteness of the sum and so on. This is the sum of these integrals, but because f of hi is 0 outside of OI, instead of taking the integral over A, we can just take the integral over OI. And now this reduces to the definition I gave above, where we just have a set that's covered by a single parameterization. Right? Each of these OI is a parameterized set, and so it reduces to this definition here, applied to f of hi. And when you apply that, that's exactly how you get this definition in 2.3. Okay, so this definition of 2.3 is just this extra step of breaking up A into pieces that are in this simpler definition I gave in these notes. Okay, and then very important, number 2.4, none of this actually depends on the trace of parameterization. This factor here means that if you use a different parameterization, the factors cancel in such a way you get the same number at the end, and it does not depend on the trace of partition of unity either. So that's very nice. So that means that this definition 2.3 actually does produce a single number on the right-hand side, no matter what choices you make for the partition of unity and for the parameterizations. Okay, so that's the definition of, or we covered, we gave an indication of what the definition of partition of unity is and the general definition for integrals over submanifolds. In this course, we don't calculate so many things explicitly, but we do use the integrations over the submanifolds, for example, to take the spherical means. These are means over spheres, and spheres are, of course, lower dimensional subsets of Rn. So if you have R3, then the sphere in R3 is a two-dimensional surface. And so to integrate over this for the purpose of spherical means requires some definition of integration on submanifolds, and so on. One of the most important results that we have coming from this is the divergence theorem, which connects an integral on a submanifold on the right-hand side with the integration over the whole of what's inside. So if you start off with an open and bounded set in Rn, and its boundary is a submanifold, then you can choose an outward pointing normal, n. So this is a vector that is perpendicular to the surface and unit length. And then we have this relationship between the two things. So we did an exercise similar to this in 11 and 12. And one consequence of this is integration by parts for multivariable functions. Okay, what do I mean by that? So let's suppose f is 0 outside of some box. All right, so we have some box that goes from minus r to r in every coordinate. And in particular, let's suppose that f has the form that it's 0 except for in the ith spot, it is equal to the function little f. So it's a function with only one component. Okay, what does that mean? That means its divergence. Remember, the divergence is by definition the sum of the ith derivative of the ith component, like so. So all of its components are 0 except for the ith component, so we just get the ith derivative of f of x. And so on the right-hand side, we have the integral over, we can make it this box, which let's just call it omega, of the divergence. Oops. So we get something like this. Actually, maybe I want to make it a product, fg. Right, so then we'll have the partial derivative of f times g, like this. And then what will we have on the right-hand side? So we'll have on the right-hand side, over the surface of the box, of f dot product with the normal, d surface integral. But by assumption, the function f is 0 outside, or we can even say on this box. So this right-hand side will be 0. Okay, and that gives us the integration by parts rule, because now we have, if we just apply the product rule to here and move it to the other side, we have the integration by parts formula. Okay, and you can see if it's not 0 outside thing, then you would have an integral on the top and the bottom plane to evaluate. All right, because it would be 0 on any of the other sides of the box. The normal points in a direction, say on the kth side, it would point in the direction with a 1 in the kth component, and then if that's not equal to the ith component, their dot product would be 0. So you would only end up with 2 sides of the box left to integrate. Let's say the top and the bottom. And then you would have you have the integral over there. But if it's 0 on all sides of the box, which is often the case, for example, when we have functions of compact support, we can always put them inside some box. Then we have this integration by parts formula that follows from the divergence theorem. Okay. One thing to note there is the the boundary of the box is technically not a submanifold, but there's a very easy generalization of the divergence theorem to sets which are the union of pieces which are submanifolds. Right. So if you look through the proof, you see that it's broken up into a local statement anyway. The proof is broken up into local statements. So as long as every point of the boundary has a neighborhood that is a submanifold, then it's okay. Yeah. Okay. So that's the divergence theorem. What follows from it is the integration of parts formula. We also use it a lot to calculate the derivatives of certain surface integrals, and to move backwards and forwards between surface integrals and integrals in Rn. It's used a lot in this course. Okay, and that concludes this first section, just revising and doing some examples with the basic notions of this course. Time to make a cup of tea.